So, in the last class we are discussing about this traffic light control using 8086. So, I have given the arrangement. So, now we have to write the program. So, I will write the program here. So, basically here I am going to use all these ports as output ports. Here you are using port A, here you are using port B, here you are using port C. Okay. Because you have to connect LED to all these ports, we have to program all the ports as output ports. Further, the instructions are you have to take 80H into AL register, then you have to out onto port A. I will assume that the port A address is FCH. So, these two instructions will program all the ports as output ports. Now, coming for this first operation, which is glow red along W and E. So, red along W and E means red along W is connected to PB0, red along W is connected to PA0. So, you have to make PB0 and PA0 as 1, so that red will be glow along west and east directions. So, for that I am taking move AL with 0 1H. I will output onto port A as well as port B. Out port A address is FCH comma AL. So, these two instructions will glow red along east direction. This will glow red along east. Similarly, red along west direction you have to output onto port B because red is connected to PV0. So, you have to out because the contents of AL remain same, FDH. FDH is the address of port B. So, this instruction will glow red along west is on. Now, what you have to do? We have to glow green along north and south, so that the passenger can pass from south to north as well as north to south. So, green is connected to PC6, green is connected to PC1 here, okay, only port C. So, what I am going to do is here port C, PC1 and PC0 should be 1, PC1 and PC6 should be 1. So, PC7, PC6, PC5, PC4, PC3, PC2, PC1, PC0. Among this, green is connected to PC1 and PC6. PC1 and PC6 should be 1s. Remaining all will be zeros because some of these pins we have used for some other LEDs along some other directions. So, that I do not want to glow those LEDs. So, what is the hexadecimal equivalent? 4 to H. So, if I write move AL comma 4 to H, if you output onto port C, port C address is FEH comma AL. So, these instructions will glow green along both north and south. Now, we have to call the delay. So, I will write the remaining program here. Call delay. This delay depends upon the traffic conditions of the particular junction. Okay. Then what you have to do is you have to glow yellow along all the directions, so that it will be alert for the vehicles crossing from north to south and south to north, they will assume that, so red is going to be glow along these two directions, and the people along west and east, they will alert, and it is a signal for them that it is going to be green on in short duration. Okay. So, I have to glow yellow along all the 4 directions. So, yellow is connected to PB2, PA2, PC7 and PC2. So, PC7, PC2 if want, PC2 should be 1, PC7 should be 1. So, the remaining all will be zeros. So, the hexadecimal equivalent of this one will be 84H. If I output 84H on port C, the yellow along north and south directions will be on, and in order to glow yellow along west and east, PB2 and PA2 has to be on. Okay. So, PA2, PB2, PB2 means this is PC, if I use this as PB, then this bit should be 1, so that means 04H. So, move AL comma 04H, so that 04H means 0000 0100. So, I am going to output onto port A as well as port B. Port A is FCH comma AL, port B is FDH comma AL. So, in this, if I assume port A, PA0, PA1, PA2, PA2 will be on if I output onto the port A, and PB2 will be on if I output onto the port B. So, these 3 instructions will glow the yellow along north and south directions is on, and to on this yellow along east and west directions, this 84H has to be sent to port C. So, we take this AL with 84H out along port C, whose address is FEH. So, this will on yellow along west and east will be on. Then you have to call another delay. I will call this as call delay, the previous one as call delay 1. So, call delay 2, delay 2 is normally less than delay 1. Then you have to reverse the operation. So, now this step is over, this step is over. Then you have to glow red along north and south, green along W and E. Then again you have to call delay, you have to glow yellow along all the 4 directions, call delay, and the same process has to be repeated. Okay. To glow red along north and south, red is connected to PC5 and PC0. So, PC0 should be 1, PC5 should be 1, remaining all will be zeros, means this should be 21H. So, if I output 21H along the port C, the red along north and south will be on. Move AL comma 21H out FE comma AL. So, with these 2 instructions, red along north and south is on. Now, you have to on the green along west and east. So, green is connected to PB1 and PA1. So, for PB1 or PA1, the content that you have to take into AL will be last but one bit should be 1, means it should be 0 to H. So, we take 0 to H, move AL comma 0 to H out onto port A as well as port B. FCH comma AL out onto FDH comma AL. So these three instructions will on green along west and east. So this is over, this is over. Then you have to again call the delay. This delay will be same as the previous delay, which is called delay 1. So this step is over. Now you have to glow yellow along all the 4 directions. Okay. So further the instructions are, these are the 5 instructions you have to use to glow yellow along all the 4 directions. Okay. So if I call these instructions as some A, I have to repeat the A here also, even including the call delay too. So this set of 6 instructions you have to repeat here. This A is set of 6 instructions, that A I am writing means here you have to replace 6 instructions. Then this will be over, this is over, then you have to repeat from the starting. So an conditional jump to up. Where should be this up? Up should be again start with this point. So this will continuously perform the task that I have given in this algorithm. Okay. This is how we can control the traffic lights along the 4 ways of a junction. Here I am taking only a simple problem where the passage is allowed from west to east or east to west, north to south or south to north. So west to south and south to east, these conditions I have not considered. Okay. So in a similar manner you can extend to, so any possible combinations, okay, that depends upon the traffic conditions on the junction. Okay. So this is about the traffic light control using 8086. Next is, if you want to connect any physical quantity, if you want to measure any physical quantity such as pressure, temperature, any other physical quantity, because this microprocessor will be very much useful in industrial applications. Okay. Nowadays also there are a lot of industries which uses the microprocessors as a controllers. Okay. So in order to measure non-electrical quantities, for the measurement and control of non-electrical quantities, using microprocessor. Any microprocessor. So we have to use 2 devices, 2 ICs called analog to digital converter and digital to analog converter. ADC and digital to analog converter. DAC. So this ADC and DAC play an important role in industrial control systems. Okay. So why you have to use this analog and digital converters, analog to digital and digital to analog converters? Okay. So what is the reason is, most of the physical quantities are non-electrical quantities. Most of the real world signals are non-electrical quantities. For example, if I take temperature. So I want to control the temperature of a furnace. This is the furnace. I want to control the temperature inside this. I want to operate over a particular range of temperatures. This type of operation is important in many industrial applications. So temperature is a non-electrical quantity. So what are the various operations that we have to do is, we can convert somehow this temperature to, so you can place a sensor here, temperature sensor, which also can be called as a transducer. A transducer is a device which converts non-electrical quantity to electrical quantity. So here the output of this one will be electrical quantity. Input for the transducer will be our sensor. This can be a sensor or transducer. Input will be non-electrical quantity, output will be electrical quantity. So this, if I take this example as RTD, is one of the temperature sensor which is called resistance dependent temperature. So this actually the principle of this one is, the resistance varies with the temperature. Resistance is proportional to temperature. If I measure this change in resistance, which is measure of temperature, how to measure the change in resistance? We can use some bridge. Okay. After that we will get some electrical quantity. Still this electrical quantity is analog. Okay. Another thing is here. So most of these things are non-electrical quantities. We can convert the non-electrical into electrical using transducer. Again this electrical quantity is analog in nature. Analog, or you can call as continuous time signals. If I want to process this continuous time signal or analog signals using microprocessor. Microprocessor is a digital device. Now we have converted non-electrical into electrical by using transducer or sensor. I cannot apply this electrical signal which is analog in nature. I cannot connect this directly to the microprocessor. So for that what is required is a to D converter, analog to digital converter. Now we will get digital data, this will be bits, this I can connect to the microprocessor. This microprocessor can be any microprocessor. So in this course we are discussing about 8086, but this can be any microprocessor. Similarly, after performing the various operations in this microprocessor, finally I have to control a non-electrical quantity. Okay. So I can send this digital signal from here. If I want to control non-electrical quantity, so this is something like, if I want to control a fan or heater. Okay. If I have a fan or heater here, I want to drive the fan. So this fan cannot be driven by using digital signals. So what you have to do is, you have to convert this digital quantity into analog by using DAC. So this is analog now, this is digital, this is analog which can be used to control the various analog appliances. Okay. That is why in between the processing is in digital domain, but the input side and the final output will be analog signals. Okay. So we need to use A to D converter and D to A converter. Now the question is how to connect this A to D converter to the microprocessor and D to A converter to the microprocessor. Okay. First I will discuss about the interfacing of this A to D and D to A converters to the microprocessor. After that, using this interfacing, I will consider some examples where the physical quantities, I will take the same example of say temperature control and measurement using microprocessor. Okay. So first I will discuss about the interfacing of ADC to the 8086. You can also call it as ADC or A to D converter. There are basically many types of A to D converters. Okay. There are basically 4 types of A to D converter. The most commonly used A to D converter in microprocessors is successive approximation type A to D converter. Because the speed of successive approximation A to D converter is more. Microprocessor is a fast device, so we have to use a faster converters. So among all the converters, successive approximation type A to D converter is faster. So most of the microprocessors uses successive approximation type A to D converter. Okay. So what is the principle of this successive approximation type A to D converter? Basically, we will be having analog signal which has to be converted into digital. So I will take the analog signal, this is analog signal VA which has to be converted into digital. Okay. So what I will do is here I will start with, if I want a 3-bit equivalent of this, I am going to use 3-bit A to D converter. So in general in most of the practical applications we will use 8-bit or 12-bit. For the explanation purpose I am assuming a 3-bit A to D converter. So I want 3-bit, this is analog signal. What is the 3-bit equivalent of digital signal? I will assume here for the sake of simplicity only VA can assume only the integer values from 0 to 7, and the corresponding digital value that I am going to expect is, this is analog, I will assume that 0 volts, correspondingly 3-bit means 0 0 0, 1 volt, 0 0 1, 2 volts, 0 1 0, 3 volts, 0 1 1. This is basically binary equivalent of this decimal value. 4 volts, 1 0 0, 5 volts, 1 0 1, 6 volts, 1 1 0, 7 volts, 1 1 1. So initially what I am going to do is, here I am going to use a D to A converter also. Inside the A to D converter there will be a D to A converter. Okay. So I will take a value to the D to A converter. This is DAC. I will compare this with the analog value using a comparator. This digital value, this is 3-bit equivalent digital value, this will be given to the comparator. Depends upon whether this analog equivalent of this digital signal is greater than or less than this VA, we will accordingly set or reset the bits. Okay. So the algorithm will be something like this. First I will start with whatever the analog voltage. I will start with 1 0 0. MSB bit I will make as 1. And this MSB 1 0 0 will be converted into analog signal which is 4 volts using DAC. Now we will compare with VA. Okay. So if this 4 volts is greater than VA, what I will do is, there are two conditions arise here. After converting this 1 0 0 into analog voltage, that is 4 volts, so this can be greater than or less than VA. Okay. So if this is greater than VA, I will keep that first MSB bit as it is, because this is still greater means the value is more than this 1 0 0. So I will keep this MSB bit as it is, then I will make second MSB also 1, third MSB will be 0. This is the case if analog equivalent of 1 0 0 is greater than VA. If analog equivalent of 100 is less than VA, that means this 100 is a larger value. So, I will reset the first MSB bit to 0 and I will make next MSB bit to 1, then 0. Okay. Now, coming over here, I will compare again the analog equivalent of this value, which is 6. So, if this value is greater than the analog value, which is to be converted into digital, I will keep these first 2 bits 1 1, I will make third bit as 1. Okay. If this value is greater than, if this is less than, then I will reset the second value and I will make third value as 1, because this is already less than. So, this 110 is less than means it is less than 6. So, I will make this second bit as 0 and then I will make this as 5. Here also we have 2 possibilities. This can be greater than or less than. This can be greater than. Greater than means I will keep this 1 as it is and I will make the next bit also 1. Less than means this 2 is less than means I will make this 2 as the second bit 1 as 0 and I will make 1. Similarly, now we have 3 things, 2 here. So, if it is greater than, then I will make 1 1 1 as it is, because I have only these 3 options, only this option only. Then the other option is if it is less than, I will make 1 1 0. Here also we have 2 things, either I can keep these 3 bits as it is 1 0 1 in case if it is greater than or equal, and otherwise I will make third bit as 0. Similarly, here I can keep this value as it is 0 1 1 or 0 1 0. Here also I can keep this value as it is, which is 0 0 1, or I will reset the last value 0 0 0. Now, here you see all the 8 possibilities are there. Okay. So, like that it will converge here. Let us assume that the given analog voltage is, say for example, 7 volts. Okay. Now, what is the flow? First I will take this 4. So, 4 is less than. Okay. So, I have to make this is less than and this is greater than, this is less than, this is greater than. Similarly, this is less than, this is greater than. So, 4 is less than, so I will go to 110, 6. 6 is also still less than, I will go to 7. Okay. This will be stopped here. Okay. If I take, say for example, this is some 2 volts, then first I will take the 4 is greater than 2, so I will go to this one 2 is equal, so I have to stop here. Okay. So, this will remain 2 only. So, after that we will not go and we will stop here itself. Okay. So, the 2 is coming here as 2. Okay. So, like that we can find out the 3-bit binary equivalent of the analog signal. This is the principle behind successive approximation type A to D converter. Okay. So, the conversion time here will be more. Now, there are different ICs for this A to D converters. The ICs of A to D converter will be of the order of 080X. X varies from 0, 1, 2, 3, so on up to 5. Means it can be 0800, 0801, 0802, 0803, 0804 or 0805. Okay. So, if I take the interfacing diagram of A to D converter to microprocessor, this A to D converter I am considering here 0804. It is a 20 pin IC with the signals represented by this. This is ADC 0804. Okay. So, the different signals are, we have a data bus, because this is 8-bit A to D converter, this is 8 bit A to D converter. So, input is analog value, output will be digital value, this is 8 bit D7 to D0, this is 8 bit digital output. And you should have some analog signal. So, analog signal will be, we have two analog signals, this is one is called V in plus, another is called V in minus. Here this thing is V in plus and V in minus, two inputs are the analog signals, two V in minus, these are called analog inputs. Why two signals are required is, so the given input signal can be either positive or negative, or it can be a differential signal. Okay, we can apply the sinusoidal type of signals also. Okay, so if the input analog input signal is only positive, I want to convert only the positive values into digital equivalent. What I will do is, I will connect the input to the V in plus, at V in plus we will connect the input, analog input, which is to be converted into digital, and simply V in minus is to be grounded. This is the case if you want to use the positive input. If the input is negative, I want to only convert the negative analog signals into corresponding digital equivalent. Then the reverse, analog input has to be connected to V in minus and V in plus has to be grounded. If I want to use input is differential, if the input is differential, means it will be having positive values as well as negative values. Then I will connect that between V in plus and V in minus. Here I will connect the input signal. Between V in plus, plus to plus, minus to minus. Okay. Here I am assuming that V in minus I am going to ground this along with some other signals. Means that I want to use only for positive signals. V in is input signal is positive. Okay. Then in addition to this, A to D converter requires some clock. The time taken to convert this analog signal to digital signal is decided by clock. Clock has to be connected between the two pins. One is called CLKR, clock R. You have to connect externally R and C, which is going to decide the frequency of this particular clock, CLK in, if this is R and this is C, then the frequency of this clock is decided by frequency is equal to 1 by 1.1 RC. By properly choosing these R and C values, we can find out the frequencies. Similarly, this will have some chip select signal that also has to be grounded. In order to perform any operation, chip select has to be grounded. This is chip select signal. This also I am connecting to ground, common ground. And we have read bar signal. This also have to ground for read operation. Whenever this conversion is over, we have to read the digital data here. For that, RD bar should be 0. And then we have two grounds. One is called analog ground, another is called digital ground. This is A ground, this is D ground. totally 5 signals we are going to ground here. One is V in minus, chip select bar, RD bar, analog ground and digital ground. So what is the reason for using the two grounds, analog ground and digital ground? Because this is a mixed signal device, this is a mixed signal device. We have analog signal as well as digital signal, mixed signal circuit. So that is why we have analog ground as well as digital ground. Okay. If I use two grounds, it will reduce the noise. That is the reason why we will use two grounds. Okay. Coming for the other side, we have one right bar signal also. So this right bar signal will act as start off conversion signal. I will explain this right bar signal, and then we have INTR signal. This right bar is output signal, INTR is input signal, and then we have V reference by 2. This is normally made open. If this is open, this will assume VCC, which is normally 5 volts. If I want to use other voltage here, we have to connect these two. If I want to operate a maximum voltage of 4 volts, you have to connect here 2 volts. If I want the maximum voltage of 2 volts, you have to connect 1 volt. This is V reference by 2. Okay. Now coming for the connections to this 8086, so you have to connect to through 8255. We know that. So any IO device has to be connected through 8255. This is 8255. How to connect this 8255 to 8086? We discussed it in the earlier classes to 8086. Then this digital has to be connected to 8255. He is also having 8-bit data bus. I will connect just simply these two data bus together, so that the data transfer can be takes place between ADC and 8255. This is D7 to D0 of 8255. So earlier you have discussed it, there is a 8-bit data bus there also. Okay. I will connect this to one of the ports of 8255. I will say use port A. I will connect this to port A of 8255 whose address is FCH. Then I will connect this to one of the pins. This is a single signal. I will call as this one as some PC3. This I have to connect as input port. This is going to be input port, and this has to be output port. This I will connect to PC7. It's up to you. Okay. Here the operation is basically, first the microprocessor has to be initiate. From here microprocessor connection is there. So this will start conversion through this 8255. Okay. So this is reverse. This WR bar is output pin and INTRB is input pin. This is output, this is input. So this is input pin. So the operation here is WR bar will act as start off conversion signal. Start off conversion signal. So whenever the microprocessor want to read some data from the A to D converter, so what the microprocessor will do is, first the microprocessor will initiate ADC through start off conversion signal. So here in this particular ADC 0804, if I apply a low to high transition, then the conversion will start. Whenever this WR bar is low, this ADC will be reset. Whenever it goes to high, this will start conversion. Okay. So low means this will reset the ADC, this will reset the ADC, and whenever this is high, conversion begins. So after the conversion is over, this INTR signal becomes 0. INTR bar becomes 0. INTR bar becomes 0 once the conversion is completed. This is the process. Now I will write the program to read the digital equivalent of this unlock value into say some register or some location, it is up to you. Okay. Suppose if I want to take digital equivalent of this one into some register, say the digital equivalent of this value I want to take into register say BL. BL I want to store the digital equivalent of the given unlock signal. So for that we have to write the program using 8086 instructions. So the first part of the program will be initialization. So you have to program this port A as input port. This is going to take the data. Port A should be input port and this should be output port. Port C, this comes to lower, port C lower. Port C upper has to be input port. So what is the control load register for this? So if I take the control load register, the last bit is port C lower, this should be output 0. Then port B we are not using, I am using as output port. Mode selection for port B I am using mode 0. Then port C upper, this should be 1 because port C upper we are going to use as input port. And this is port A has to be used as input port, so this should be 1. Mode selection for port A is I am going to use in mode 0, and then this is mode control which signal which is equal to 1. So what is the corresponding hexadecimal? This is 98H. If I enter this 98H into the control register of this 8255 whose address is FFH, then this will set port A as input port through which the data will be read, and port C lower as output port, port C upper as input port. This is the first instructions. So move AL comma 98H out, control register address is FFH comma AL. So these two instructions will set port A as input port in mode 0, port C lower as output port, port C upper as input port, all in mode 0. Okay. So after that what you have to do? You have to start the conversion, means you have to first make this signal, you send here low. Okay. Then after that you have to send high. Then the conversion will start. After that you check this signal, input signal. If this input signal is 0, means conversion is over. If this is 1, you have to wait until this is equal to 0. Once this is equal to 0, you simply read the data. That is the procedure. Okay. So first I want to send a low over this PC3 and then high over PC3. So what is the instructions for that? Low over PC3. PC3 means PC7, PC6, PC5, PC4, PC3, PC2, PC1, PC0. So because I am using PC3, PC3 should be initially 0. So I can make all zeros. So, we can take move AL comma 00H, out port C address is FEH comma AL. This will make all the pins of port C as low, but I want only the PC3 which is equal to, which is connected to right bar. This will becomes low. A low to high transition is required. So, what is the time between the low to high transition? A small amount of the time, which is the time taken to execute these instructions, is enough. So, no need of delay routines here. Then I will make move AL comma, I want only PC3 is on, means this should be 08H, out FEH comma AL. Now what happens, PC3 will be WR bar which is equal to high. So, there is a high to low transition. What is the transition time? The transition time is to execute this and this instruction. That time is enough to activate the A to D converter. Okay. Now the conversion will start. I have to check whether the conversion is over or not. So, conversion, end of the conversion signal which will act as a NTR signal which is connected to PC7. I have to check PC7. If PC7 is 0, conversion is over. If PC7 is 1, conversion is not yet over. So, I will input the contents of port C. So, the instruction will be in AL comma FEH. And we have to rotate left ROL AL comma 01. In AL we will be having port C contents. So, in that MSB bit is PC7 which is connected to, so when we are checking here, PC7 bit will comes into carry. Jump on carry. If carry is there, what does it mean? If this is 2, jump on carry, wait. Jump on carry means PC7 is 1, means conversion is not over. PC7 which is equal to INTR bar 1 means conversion is not yet over. So, I will just simply wait. Where you have to wait? We have to input this. Again you have to input this and you have to rotate for the MSB bit. You can use here ROL or RLC also through carry. So, when does it will come out of this loop is whenever PC7 is equal to 0 which is equal to INTR bar. Whenever this is equal to 0, this will come out of the loop, means conversion is over. Now, where the data is available? In port A. So, you have to read that port A. In AL comma port A address is FCH. I want to store this data into BL register. So, you can move contents of AL onto BL. You can stop. If you want to read only once, if you want to continuously read, instead of alt you can write jump to up. This up is again this. So, in this way you can read the digital equivalent of the analog signal using ADC. Okay. So, I will see the more details like how the conversion has to be takes place and what are the exact digital equivalent of the analog signals and what is the resolution of A to D converters in the next class. Thank you.